If you are driving a Toyota, Honda, Mazda, Subaru, Nissan, Lexus, or Acura built in the last 20 years, there is a sensor sitting inside your engine bay right now that costs nothing to service, takes under 15 minutes to clean, and if left dirty, data published by the U.S. Department of Energy's fueleconomy.gov resource indicates your engine may be burning significantly more fuel than it was engineered to use. Not because of a mechanical failure, not because of a leak, not because of anything a dealer would detect on a standard diagnostic scan without specifically looking for it, because of a layer of contamination thinner than a human hair, sitting on a wire the size of a sewing needle. The mechanic in this thumbnail is holding two versions of that sensor, one clean, one coated in oil vapor and road contamination. That spray can on the hood costs under $12 at any auto parts store. What a dealership would charge you to service this problem, and whether they would tell you the solution does not require replacing anything at all, is what this video is about. Before we go further, if you own a Japanese car and you are tired of paying the service industry to fix things you can handle in a parking lot, subscribe now and share this with the person in your life who just handed a service advisor $250 for a sensor job that required a $10 can of spray and 15 minutes of their time. And if you want the full maintenance guide behind everything we cover on this channel, the Japanese vault is linked in the description. Now, the sensor in question is not the oxygen sensor. It is not the throttle position sensor. It is not buried behind the intake manifold or accessible only with the engine partially disassembled. The mass airflow sensor, the MAF, sits in the open air intake path between your air filter housing and your throttle body. On the majority of Toyota, Honda, Mazda, and Subaru applications built after 2000, it is accessible with nothing more than a flathead screwdriver and a 10mm socket. It is one of the most important data inputs your engine computer uses every single time combustion occurs, and it is one of the least maintained components on the average Japanese car driven in North America or Europe. Here is why it matters, and the mechanism is worth understanding before you touch anything. The hot wire MAF sensor works by heating a very fine wire, typically platinum or nickel iron alloy, suspended inside the intake tube to a precise temperature above the ambient air temperature. As air flows past that wire, the moving air carries heat away. The engine control unit monitors the amount of electrical current required to maintain that wire at its target temperature. Greater current draw means greater air mass flowing into the engine. The ECU uses that air mass reading, combined with engine speed data from the crankshaft position sensor, to calculate the precise fuel injection volume required to reach the target combustion ratio, 14.7 parts air to 1 part fuel at idle and light cruise, the stoichiometric ratio at which a catalytic converter operates at peak efficiency and combustion is most complete. When that wire becomes contaminated, and it will, on every engine with more than 40,000 miles, the thermal exchange properties around the sensing element change. Contamination comes primarily from three sources. First, oil mist circulating through the positive crankcase ventilation system, which returns blow-by gases from the crankcase back into the intake stream and deposits a fine aerosolized oil film on everything downstream of the PCV port, including the MAF wire. Second, fine dust particles that pass through degraded or incorrectly seated air filter media. Third, silicone vapors released during the initial curing period of aftermarket intake hoses and airbox gaskets. The combined effect is a wire that no longer exchanges heat accurately with the passing airstream. In the most common real-world contamination pattern, where PCV oil mist is the primary source, the sensor begins to underread the actual air mass entering the engine. The ECU receives a signal indicating less air than is actually present. The ECU then attempts to compensate using fuel trims, the adaptive correction values, split into short-term and long-term tables that the ECU continuously updates based on feedback from the downstream oxygen sensors. As long-term fuel trim values climb to compensate for the perceived air-fuel imbalance, the engine is injecting more fuel per cycle than it would with an accurate sensor reading. According to the U.S. Department of Energy's published fueleconomy.gov data, a faulty oxygen sensor alone can reduce fuel economy by as much as 40%. The MAF sensor, which sits upstream of the oxygen sensor and establishes the primary fuel calculation before the oxygen sensor can provide closed-loop correction, compounds this effect under contamination. Independent testing and analysis by members of the Society of Automotive Engineers, including technical papers published in SAE's automotive engineering literature, have documented measurable fuel economy degradation in vehicles operating with out-of-specification MAF sensor output. So why does this not appear in the service advisor's standard inspection sheet? The answer is not complicated, and it is not a deliberate secret. It is incentive structure. According to IBISWorld's market research on the automotive repair and maintenance services sector in the United States, the industry generates approximately $74 billion in annual revenue. The margin structure of that business is built around three revenue categories: parts markup, labor hours billed, and diagnostic fees charged. A cleaning procedure requiring $12 of product, 15 minutes of technician time, and 0 parts on the invoice generates a fraction of the margin that a full sensor replacement, a diagnostic scan fee, and an associated air induction service generates. This is not a conspiracy. It is the same incentive structure that exists in any service industry where the diagnosis and the remedy happen at the same counter. The service advisor is compensated on service revenue, not on your long-term fuel economy. The cleaning protocol exists in factory service documentation. It exists in the engineering literature published by Bosch, by Denso, and by Hitachi, the three primary MAF sensor suppliers to Japanese automakers. It simply does not make its way into the service lane conversation because it does not generate the transaction size that serves the business model. The history of this sensor makes the economics even clearer when you follow the engineering timeline from the beginning. In 1974, the United States Congress passed the Energy Policy and Conservation Act, which established corporate average fuel economy standards for the first time and forced automakers to move toward precision fuel metering systems. The carburetor, which estimated intake air volume by measuring pressure drop across a venturi tube and translated that into fuel delivery through mechanical jets and float bowl circuitry, was too imprecise for the closed-loop electronic fuel control systems that new emissions and economy mandates required. Robert Bosch GmbH, building on their 1967 D-Jetronic fuel injection system and the subsequent L-Jetronic system introduced in 1973, developed and patented the hot wire mass airflow meter in the late 1970s. According to Bosch's own published history of their fuel systems division, the hot wire MAF entered series production in 1980 on the Mercedes-Benz 280E, replacing the vane-type airflow meter that had been used in earlier L-Jetronic applications. The technology transfer to Japanese manufacturers happened rapidly over the following decade. Toyota's engineers, already deep into their own electronic fuel injection development under the EFI program that debuted on the 1979 Toyota Soarer in the Japanese domestic market, incorporated hot wire MAF sensor technology across the Corolla and Camry platforms through the late 1980s. Denso Corporation, Toyota's primary sensor and electronics supplier, became the dominant Japanese market manufacturer of hot wire MAF sensors and remains so today. Honda followed with their PGMFI closed-loop fuel injection systems across the Civic and Accord lineups. Mazda, Nissan, and Subaru all transitioned to hot wire MAF sensor-based fuel management through the same period, and by 1995, the hot wire MAF was the universal standard across virtually every Japanese production engine sold in Western markets. The same sensor architecture that Bosch developed for European luxury sedans in 1980 is sitting in the air intake of a 2015 Toyota Camry, a 2018 Honda Accord, and a 2020 Mazda CX-5 today. Denso Corporation published internal engineering guidance as early as 1990, acknowledging contamination as a known and expected performance degradation pathway in hot wire MAF sensors, and recommending periodic inspection and cleaning as part of ongoing maintenance. That documentation exists in Denso's technical publications archive. It never translated into the wallet card service schedule that ends up in a glove box. The parts replacement and distribution business, not the maintenance education business, is where the revenue lives. Now here's the procedure. This is the part of the video where everything the thumbnail promised gets delivered. You will need 1 can of dedicated mass airflow sensor cleaner, not carburetor cleaner, not brake cleaner, not general electrical contact spray. The critical distinction is this. Brake cleaner contains chlorinated solvents that will destroy the platinum wire or hot film substrate permanently, requiring a full sensor replacement that will cost between $160 and $280 depending on your vehicle and whether you use OEM or aftermarket parts. MAF-specific cleaner is formulated with a fast-evaporating hydrocarbon base that dissolves oil and carbon deposits without leaving any residue and without attacking the sensing element or its support structure. CRC Industries manufactures the most widely distributed version in North America under the CRC Mass Airflow Sensor Cleaner label. The current retail price at AutoZone, O'Reilly Auto Parts, and Advance Auto Parts sits between $8 and $12 depending on location and promotions. 1 can is sufficient for 2 to 3 cleaning sessions. The precondition before you begin is that the engine must be fully cold. A cold engine means the metal has contracted back to ambient dimensions, connectors release cleanly without heat-expanded resistance, and critically, you will not be reintroducing a still wet sensor into a running engine. 15 to 20 minutes after the last engine operation is sufficient at normal ambient temperatures. Do not rush this step. Location and access varies slightly by platform, but the procedure is the same. On Toyota Corolla and Camry models from 2003 to 2024, the MAF sensor is mounted in the intake tube approximately 8 inches downstream of the air filter box, secured by 2 Phillips head or JIS screws, with a 2-pin or 4-pin harness connector, depending on year. On Honda Civic and Accord applications from 2006 onward, the sensor is integrated into the top of the air cleaner housing and is accessible after releasing the intake resonator hose clamp with a flathead screwdriver. On Mazda 3, 6, and CX-5 models with Sky Active engine architecture, the MAF is incorporated into the air cleaner assembly cover. On Subaru Outback and Forester models, the sensor sits in the intake tube between the airbox outlet and the throttle body, and requires releasing one hose clamp for access. Regardless of platform, none of these require lifting the vehicle, removing panels, or any specialized tools. Disconnect the negative battery terminal first. Wait 2 full minutes. This step matters because it allows the ECU to release any volatile adaptive memory states before the sensor harness is disconnected, which prevents the ECU from locking in erroneous baseline values during the cleaning period. Press the release tab on the harness connector and pull it directly rearward, never twist or lever it. Remove the 2 retaining screws and withdraw the sensor from the intake tube carefully, keeping your fingers away from the sensing element at all times. Skin oils from your fingertips will add to the contamination problem you are solving. Hold the sensor so the sensing element faces upward or to the side, never face down, as contamination and cleaner can drip back onto the element. From a distance of 2 to 3 inches, apply 3 to 4 short bursts of MAF cleaner, each lasting approximately 1 second. You will see the cleaner dissolve and carry the brown or gray oil contamination away from the wire or film surface. Do not use a brush, a cloth, or compressed air to accelerate or assist the cleaning. Any physical contact with the sensing element will damage it. Allow the sensor to air dry completely. 10 to 12 minutes at normal room temperature is sufficient. Then, reinsert the sensor, tighten the retaining screws to hand tight plus a quarter turn, press the harness connector home until the tab clicks, reconnect the battery negative terminal, and start the engine. Allow the engine to idle for 5 minutes before driving. Over the following 50 to 100 miles, the ECU will relearn its long-term fuel trim values back toward the calibrated baseline the clean sensor now provides. For maintenance intervals, the guidance in Toyota's published service documentation for the Corolla and Camry specifies air filter replacement at 30,000 miles under normal conditions and 15,000 miles under severe conditions, short trips, dusty roads, extended idling, or towing. A healthy, uncompromised OEM specification paper air filter element is the primary barrier against MAF contamination. Cleaning the MAF sensor at every second air filter change, so approximately every 60,000 miles under normal conditions, keeps the sensor output within the accuracy window the manufacturer's fuel management calibration was designed around. The fleet operations data on this is the most concrete evidence of long-term value. Fleet maintenance programs for municipal vehicle fleets, including those reported in the American Public Works Association's Fleet Management Guidance publications, have incorporated MAF sensor inspection and cleaning into scheduled preventive maintenance intervals for high-utilization vehicles operating in urban stop-and-go driving conditions. The documented reason, stated in fleet budget justification language, is fuel economy preservation across high-mileage units where per-vehicle fuel costs are tracked against baseline benchmarks. When fuel trim drift is detected during OBD2 fleet scans, cleaning the MAF sensor is the first corrective step before sensor replacement is authorized, because cleaning resolves the majority of contamination-related drift cases at a fraction of the replacement cost. According to RepairPal's aggregated service pricing data, a MAF sensor replacement at a dealership for a Toyota Camry currently averages between $220 and $280, including labor. That is, a parts replacement on a component that, in the majority of contamination cases, did not need replacing. It needed cleaning. The $12 can of MAF cleaner and the 15 minutes you spent this weekend achieved the same ECU recalibration outcome the dealer would have billed you $250 to provide. You now understand something that most drivers who have owned Japanese cars for decades have never been told directly. The MAF sensor is not a mysterious internal component. It is a wire, a support structure, and a circuit board in a plastic housing sitting in an accessible location in your intake path. It gets dirty over time through normal engine operation. It can be cleaned without any mechanical skill beyond the ability to release a hose clamp and press a connector tab. The chemistry required to clean it correctly costs less than a tank of the extra fuel the dirty sensor is causing you to burn. The knowledge to do it safely, the correct product, the cold engine requirement, the ECU memory reset, the dry time, was in factory engineering documentation and fleet maintenance protocols for decades before it was available to a private car owner through a channel like this one. The gap between what service economics make visible to you at the counter and what the engineering documentation actually recommends has never been about complexity. It has always been about who benefits from you not knowing. If you found this useful, subscribe. Every video on this channel is sourced from the same layer: factory service documentation, SAE technical papers, manufacturer engineering archives, and fleet operator records. No filler, no speculation, no product placements. Just the maintenance knowledge that extends the life of your car and keeps the money in your account. Share this with someone you know who drives a Toyota, Honda, Mazda, or Subaru and has never heard the words mass airflow sensor. The $12 they spend on a can of CRC cleaner this weekend may save them the next service invoice they were about to accept without question. The next video covers what Toyota's own factory service documentation says about engine oil viscosity selection for high mileage applications. And if your Camry or Corolla has crossed 80,000 miles, the viscosity listed in your owner's manual may be working against your engine clearances, not for them. That is the next vault. And if you want the full maintenance guide behind everything we cover on this channel, the Japanese vault is linked in the description.